There are few rocket engines more iconic than the RS-25, also known as the Space Shuttle main engine. Even though it's been around in some form since the 1970s, it's been improved and upgraded several times, making it the most efficient liquid fuel rocket engine going today. And now the RS-25 is going to see a new chapter in its history, working to carry NASA's new space launch system back to deep space beyond Earth orbit. When you really think about it, the principle of a rocket is actually pretty simple. Use a combustible fuel to blast out a jet of hot gas through a nozzle. Rockets take advantage of Newton's third law. For every action there's an equal and opposite reaction. As material is fired out the back of the rocket at supersonic speeds, the rocket receives a force, pushing it in the opposite direction. Unlike jet engines, which need to bring in oxygen to carry out the combustion, rockets carry their own oxidizer, so they can even work in the vacuum of space where there is no oxygen. Rockets aren't pushing against anything, they're throwing material out the back so fast that they move in the opposite direction. Now, there's so many different kinds of rockets out there on the market. There are the small sounding rockets that can follow a parabolic trajectory, reaching a high altitude and then returning to Earth. And then there are the enormous multi-stage rockets like the Atlas or the Ariane, capable of lifting tons of satellite cargo into low Earth orbit and beyond. And of course, there's everything in between, from many different manufacturers across many different nations. But there are fewer kinds of rocket engines, though. You'll see the same engine attached to different sizes of rockets. Some of these engines have been used continuously for decades, like the Russian RD-180 engine, which is used for Russian and even American launches. Others are relatively brand new, like SpaceX's Merlin engine, which has seen many different iterations carrying Falcon rockets into space, and then the even newer Blue Origin BE-4. Today, I want to talk about an iconic rocket engine, the mighty RS-25, the Space Shuttle's main engine. Let's look at its history, capabilities, and how it'll see a whole new chapter by helping to push Space Launch Systems rockets into orbit and beyond. Now, you might have some problems with the Space Shuttle program and disagree with NASA's plans for the Space Launch System, but the RS-25 is an incredible piece of space hardware. There's not much out there that can stack up to it in pure power and efficiency. As the Apollo era was winding down, NASA began investigating the technologies it would be using for its next step in spaceflight, the Space Shuttle. While the mighty Saturn V was a beast for hurling heavy cargo deep into the cosmos, the Space Shuttle was seen as a reusable vehicle that would make spaceflight a routine experience. It turns out, spaceflight wasn't ready to be routine. But NASA didn't know that yet, balancing the various requirements from different stakeholders, politicians, engineers, etc. During the design process, the shuttle went through many variations. There was a time that the Space Shuttle could have had 12 sea-level booster engines and then 3 orbiter engines, fixed wing, then delta wing. They finally settled on the modern design with the Space Shuttle orbiter attached to the huge external fuel tank with its solid rocket boosters. When it came to the new engines, new technologies were being considered, like an expanding nozzle that would operate more efficiently at different altitudes and high-pressure engines that would use the fuel more efficiently to produce thrust. When the initial contracts for the Space Shuttle were awarded in 1969, yes, work on the Space Shuttle began back when the first astronauts were landing on the Moon. NASA requested engine proposals that matched the capabilities they'd been studying, with the ability to throttle the engine, expanding nozzles, and a very high-pressure combustion chamber. The contract was awarded to Aerojet to produce the Space Shuttle main engine, the RS-25, and the company later merged in 2013 with Pratt & Whitney Rocketdyne to become Aerojet Rocketdyne, which I think is the coolest name for a rocket company. The Space Shuttle was equipped with 3 RS-25 engines, which were fed by liquid oxygen and hydrogen from the huge orange external fuel tank. Together with the twin solid rocket boosters, the Space Shuttle's 2,000 tons, or 4.4 million pounds, would be carried into orbit. Each shuttle would be capable of delivering 27,500 kilograms, or 60,600 pounds of cargo to low Earth orbit. The actual thrust of the RS-25 is actually a little difficult to pin down. The engine was designed to be throttled so that it could change the total amount of engine power from 67% to 109% of its power rating, and in an emergency it could probably hit 111%. At sea level and 100% thrust, each engine could generate 380,000 pounds of thrust, or 1,670 kilonewtons. And in a vacuum, they could produce 470,000 pounds of thrust, or 2,090 kilonewtons. But like I said, the rockets could be throttled up beyond 100%, which I know sounds kind of crazy, but 100% was the original spec, while they were able to get the engine power higher through improvements and modifications over the engine's development lifetime. Need some kind of comparison? The SpaceX Merlin engine produces 190,000 pounds of thrust, or 845 kilonewtons, rising to 205,500 pounds of thrust, or 914 kilonewtons, when it reaches the vacuum of space. And that's why the Falcon 9 has the name. It carries 9 Merlin engines, and the Falcon Heavy has 27 of them. Over the course of the shuttle program, there were a total of 46 RS-25 engines used. And together, they successfully lifted off the Space Shuttle 135 times. One RS-25 did fail on a 1985 mission with Challenger, but the shuttle was still able to get to orbit and complete its mission with the one failed engine. And there were a handful of times when leaks and sensors connected with the engines led to like a launch delay. And then 1 year later, Challenger was destroyed along with its 7 astronaut crew during launch. And the mishap was traced back to the O-rings that helped attach the solid rocket boosters. Just to give you a sense of scale, each RS-25 measures 4.3 meters tall, and the nozzle is 2.4 meters in diameter. It's about the size of a car. There are 4 turbo pumps that pull in liquid hydrogen and liquid oxygen from the main fuel tank and then force them into the combustion chamber at high pressure. Inside the combustion chamber, the fuel and oxidizer are mixed together and ignited. Beneath this is the huge nozzle where the hot gases are expelled at 13 times the speed of sound. The RS-25 is known as a staged combustion engine, where turbine exhaust is captured and fed back into the engine, and this makes for higher performance, but also higher pressure and more danger. And during its initial development, NASA had a rough time getting the RS-25 to handle the pressure and the forces involved. And this is one of the key differences from other engines on the market, like the SpaceX Merlin, which is open cycle. It's less powerful, pound for pound, than the RS-25, but you get the benefits of lower cost and higher production rates. Each Falcon Heavy will have almost as many Merlin engines in it as the number of RS-25s that were ever built. The end of the shuttle program would have been the end of the RS-25 engine, but it's gotten a new lease on life with NASA's Space Launch System. And I'm going to talk about how the RS-25 fits in, but first I'd like to thank Howard Amos, Bjorn Carlson, Epix911, Jonathan Steen, Anders Thordarson, and the rest of our 802 patrons for the generous support. If you love what we're doing, you want to get in on the action, head over to patreon.com/universetoday. Once the shuttle program wrapped up, NASA was ordered to keep the fleet's workforce employed, developing the Ares rockets for the Constellation program. This transitioned to the Space Launch System, which would give NASA heavy lift capabilities again, enabling missions past low Earth orbit, to the Moon, asteroids, and beyond, eventually to Mars. In its initial Block 1 design, SLS will be capable of lofting 70 metric tons to low Earth orbit, and the final Block 2 configuration will be able to carry 130 metric tons. In fact, it could end up being even more powerful than the Saturn V, making it the most powerful rocket ever built, until the SpaceX BFR becomes operational. And much of this depends on using the RS-25 engines for the central core of the Space Launch System's first stage, since they have 16 left over from the Space Shuttle days. Unlike the Space Shuttle, the SLS will be equipped with 4 RS-25s instead of 3, together contributing 2 million pounds of thrust, or 9,000 kilonewtons, to the system. This will be joined by the twin solid rocket boosters for a total of 8 million pounds of thrust, or 32,000 kilonewtons. As part of the upgrade to SLS, NASA engineered an entirely new engine controller to match the engine with the new rocket. At the end of 2017, NASA wrapped up a 400-second test of its new RS-25 controller. This was the 8th test of the year so far, and the 6th using this new controller. There's already been a successful test in 2018, with many more to come. So if all goes well, the RS-25 will see its return to flight when the first SLS rocket blasts off with Exploration Mission 1, now scheduled for 2019, or maybe 2020? Unlike the reusability of the shuttle though, the core stage of SLS will be destroyed after launch, including its RS-25s. And once they use up this initial group of leftover engines, they'll need to get more from Aerojet Rocketdyne. While the RS-25 engines were developed and built for the shuttle fleet, and now SLS, they've been upgraded several times, with the total power output updated to 105% by the end of the shuttle program. SLS should get to 109%, and they think they can push the engines to 111%. Now normally, this would mean a decline in their reusability, but these engines won't be reused, so they might as well be driven to the max. Each mission using the Space Launch System is going to cost US taxpayers $500 million to $1 billion. A launch on the SpaceX Falcon Heavy is going to cost $90 million in comparison. And although it won't have the raw launch capacity of the SLS, it's going to be a lot cheaper. Each RS-25 probably cost NASA around $60 million. And for that much money, you could get a flight on a Falcon 9. So I think there's a really important argument to have about the cost effectiveness of the SLS and developing a rocket system that gets destroyed with every launch, now that SpaceX and Blue Origin are demonstrating reusability. But I've really got to admire the power and capability of the RS-25 and the creativity and workmanship that went into it. It'll go down in the history books as one of the most important and impressive rocket engines ever built, and I can't wait to see it fly again. How do you feel about the RS-25, the Space Shuttle, and the Space Launch System? Did you want me to compare this engine with the more modern reusable rockets from SpaceX and Blue Origin? Let me know your thoughts in the comments. Now, do you want more space news? I'm now writing a weekly email newsletter that highlights many of the big stories that happened this week. It's quick, easy to digest, with lots of amazing pictures and videos. You can find out more and sign up by going to universetoday.com/newsletter. In our next episode, I continue my series on the discoveries made by space missions. Now, what did NASA's Curiosity rover discover? That's next time. And finally, here's the playlist.